In this lesson, we will understand the impact of distracted drivers. What does it mean to be distracted? How do you think being distracted may affect whether or not you will avoid a collision? Watch the videos of the car braking when the driver is undistracted and when the driver is distracted. What differences do you notice? This is the video of the not distracted driver. And this is the video of the distracted driver. We will use a strip of paper to create a position line. For the first video, let's identify which is the undistracted driver. Let's mark the important positions that can help us analyze the way the car moves. Let's consider these 4 positions. At position 0, the car appears. At position 1, an obstacle appears. At position 2, the brake lights go on. And at position 3, the car stops completely. So now the car has appeared. Let's back up the frames. I want to measure the car's rear tire. Okay, here is position 0. I can see the car's rear tire at this point. We're going to say delta x for its position along the x axis. Now, let's stop the video when the obstacle appears. Notice the cone that appears around this area. There's the cone. Let's back it up. Frame by frame. Okay. And I'll try to pause it exactly. It was a little before that. Okay, that's about the best I can do, pausing the video at the right time. So this is position 1. Now, when do we see the brake lights go on? Let's continue the video. I see the brake lights here. Let's back it up around this white truck. See if I can catch the exact moment. Do I see brake lights in this frame? It's very hard to see. Let me adjust the light in the room a little. Now I've darkened the room and I can see the brake lights clearly on at position 2 right here in front of this white truck. Now position 3, the car comes to a complete spot at this position. Delta X3. Now I have my 4 positions. Now, what happens to the car during this interval of time? Correct. That's when the driver reacts to seeing the obstacle. So let's call it the reaction distance. From position 1 to position 2. Now what happens in this interval between seeing the obstacle and putting on the brakes and stopping? Also correct. This is the braking distance. Let's label it as such. Braking distance. Let's measure those 2 intervals. The reaction distance from point 1 to point 2 is 24.5 centimeters. The braking distance from point 2 to point 3 is 11 centimeters. What information do we need to calculate the actual distances in real life between the positions that we identified? Let's hear some of your thoughts. What distances should we calculate? That's correct. Let's definitely calculate how large the car is in real life, so we can use that as kind of a scaling ratio to calculate the actual distances of these other distances. What model of car is this? I looked it up. The model of car that this is 4.5 meters long. The car is 4.5 meters. Let's see if we can use that to determine the actual real life distance. From bumper to bumper, this car is 23.5 centimeters long, or 23.5 centimeters on my projection to the screen. How would we now calculate the reaction distance and braking distance in real life? Let's do that on our handouts. Let's find the length of the car at the scale that we watched it and record that we said it was 23.5 centimeters. Then let's find the length of each position interval that we identified. The lengths between the important positions at that same scale, and record those on your handout. Let's calculate a scaling ratio of the actual length of the car and use this ratio with the measured distances so we can calculate the actual distances in real life. For example, the measured reaction distance was 24.5 centimeters. Let me change markers. 24.5 centimeters. Let's multiply that by our scaling ratio determined by the length of the car times 4.5 meters for every 23.5 centimeters. First, we'll multiply 24.5 by the number in the numerator position. That equals 110.25 centimeters times meters. Now, let's divide that by 23.5 to get the value of meters when we cancel out our centimeters. What I got was 4.69 on my calculator. Which we will round up to 7. That means our reaction distance from delta x1 to delta x2 is 4.7 meters. Can you calculate the braking distance now? Now, let's make predictions of what will happen when we look at a driver who is distracted. Will the distances we calculated for reaction and braking change if the driver's distracted? How? Let's mark the same important positions that we marked for the first video on a second position line. Then we'll calculate the actual distances between those positions so we could compare across them. Let's go ahead and watch the video of our distracted driver. Ooh. Let's find the exact position when the car appears first. I'm looking for the back tire right there. Let's mark that position as delta x 0, position 0. Car appears. Am I in the frame? Oh my gosh. There. Now let's pause the video when the cone appears. Oh, let's back it up. Okay, it was right before 2.99. That's delta x1. Obstacle appears. Now, let's mark the position when the brake lights turn on. I see that the brake lights are on right here at 4.66. If I back it up one frame, then the brake lights are not on. If I advance it one frame, they're not on. They are on 4.66, 4.58, they are on. Let's go back one more frame. I'm gonna say 4449, not on. Okay, this is my best estimate that the lights are definitely on, and at 4.44, which was the closest frame I could get before this, they were definitely off. So let's mark 4.58 as delta x2 when the brake lights first come on. Now let's mark when the car stops. Okay. And the car now stops here. Position 3. Car stops. Now we'll measure these distances on the board. Remember that our reaction distance is the distance between the obstacle appearing and the brake lights coming on. I have that distance as 40 centimeters. Reaction distance. The braking distance between when the brake lights turn on and the car stopping, 13.5 centimeters. To put this now to scale so we can compare it to the undistracted driver in real world terms, remember that our car from bumper to bumper is 24.5 centimeters. So that will give us our scaling ratio, because I know that the car in real life is actually I think it said 4.5 meters long. Let's determine the distance in real life of 40 centimeters and 13.5 centimeters by using this scaling ratio. So you should be keeping track of these measured distances and scaled distances on your handout. I'm going to create this poster to help us keep track of it all together as a class. So when we measured the car in the video, it was 24.5 centimeters. In both videos. Same car. The distance from position 0 to position 1 was 16.5 centimeters. For the not distracted driver, and 17 centimeters for the distracted driver. The distance between position 1 and position 2 for our undistracted driver was 24.5 centimeters. And 40 centimeters for our distracted driver. And that was our reaction distance. Our braking distance up to position 3 for the not distracted driver was 11 centimeters. And for the distracted driver, it was 13.5. Our scaling ratio that we will use, since our car in real life is 4.5 meters long, we'll use the scaling ratio for centimeters to meters. I made a mistake in the video because my scaling ratio had my measured units in the numerator. And remember, we should always put the units that we want to end up with, our actual units, in the numerator. So our scaling ratio should actually be 4.5 because that's the actual length of the car divided by 24.5, which is our measured ratio of the car. So if that means our scaling ratio means we multiply by 0.18. Let's take that number and multiply it by the measured distances to get our actual distances for our not distracted driver and our distracted driver. Do that on your handouts. So now that we have measured our data and scaled our data to the proper ratios, you should have these values filled in. I'm not showing them to you in the video, but do them on your handout. Now, earlier on we made a prediction. How did our predictions about the distracted driver match our data? Or how are they different? Let's take a moment to think back to our earlier response. So, what was different about the way the distracted driver was driving that could explain why these distances are different. We have the driver in our car driving along. He's having fun using his cell phone. And and there's other friends in the car. And oh, hey, oh, there's an obstacle. Oh my God. And then it stops, right? The obstacle appeared way back here, right? So I wonder, how long did it take for them to react? Maybe we have to investigate some of the times as well as the distances. For your home learning, before you go to the next part of the video, take the time to read about distracted driving and how it affects how long it takes a driver to react. So, how could we really do a test to see whether being distracted impacts our reaction time? I want you to try testing your reaction times normally and when someone is distracting you. Notice that being distracted makes a big difference. Let's use this tester. How old are your reactions? I'm going to try myself. Here I go. Driving, 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 driving. Oh! Oh! I have the reactions of a 47-year-old, but I'm only 45. Now let's do it while I'm distracted. I'm going to start texting somebody on my phone while I play the game. This might get dangerous. I'm texting, I'm reading a text, and oh, that was funny, ha 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 ha. Oh! Now I'm a very, very old person. Way too old to even probably still be alive. Now let's do a timeline of events for the undistracted driver. And I have a timeline of seconds, and we will stop the video to see the time code at each of these important moments during the video. When the car appears, and I'm focused on the back tire in the frame to get that precise. Before 216. Okay. So at 2 seconds, 16 seconds, 2.16, we should note time 0. When the car appears. Now let's find out the next position when the obstacle appears. Right before 3.33. Let's see.
2.95, still there. 2.66, not there. 2.87, still there. So at about 2.9, about 2.9 is as close as I can get the video. Let's just call it 2.9 because I don't have super fine detail over the video control. But the obstacle is clearly not there at 2.87. It was there at 2.95. So we'll call that time 1. Let's guess 2.94, just to be safe. Now, when do the brake lights come on? It was right while the truck. Right there. Before the truck. So I see 3.95 as the brake lights coming on. It's probably a little bit before that. Let's call that time 2. Time 3. Brake lights on at 3.7, about 3.7 seconds. Brakes on. And when does the car stop? It's definitely stopped there. It seemed to be a little bit sooner than that. Let's call time for 5.04 seconds. It's right after 5 seconds. Time for car stops at about 5.04 seconds. So, what do you think we could do to visualize what's happening in both time and position to see a relationship for both of those things? Good idea. Let's make a graph. To think about how to set up our graph with an x-axis and a y-axis, we should first consider which of these variables determines the other variable. Does time determine the position, or does the position determine the time? So since we can't really change time, it's more likely that time, whatever time it is in the video, determines what position the car is in. So let's establish time on our x-axis, and then we will establish the distances on our y-axis. So now, how can I represent the position and time? I'll have to determine the points on my graph. Okay? So, go to this. Let's blank this out for now. So at time 0, the car appears, and its position is right here at this point. So I might say that that position 1, I am at how many meters? Let's graph the actual distances. Let's plot all of these points on the graph. We're going to plot T0 and X0, T1 and X1, T2 and X2, and T3 and X3. Using my grid lines here, I know that this would be our first point where the car appears. T1 is right here. My next point would be right here. T2 would be right here where the brakes come on. And that's T2 on my y-axis. And T3 is where the car stops. Connect these points with a line. Mark your points on the graph. So now, to help us think more clearly about what this graph is showing us, let's consider the speed of the car. In math terms, we call this the slope of the line, or how much the y-axis changed every time the x-axis changed. We're going to write that as a fraction from that says the distance over the time, since slope of the line is always rise over run, so we always put the y-axis value over the x-axis value. Let's consider the first interval of our graph, from when the car appears to when the obstacle appears. And that distance is 3 meters from from T0 to T1. And that time interval is from 2.16 to 2.94. So that is let's see, if I subtract 94 minus 16, I'll get my answer. 78. So that's 0.78 seconds. This is called slope of the line over interval delta x1. Now we can see how fast the car is traveling in terms of meters per second. So with my calculator, 3 divided by 0.78, we should get something about 3.8 meters per second as the speed of the car. Now let's take a closer look at what this slope is telling us. So when I calculate the time interval between T1 and T2, it's 0.76 seconds. And the car's distance here, change along the y-axis, is 4.4 meters. That means this car, in time interval delta x2, is 5.8 meters per second. Which means that it actually sped up after the obstacle appeared and before braking. Now we can see when it's braking, its speed does, the slope changes. It changes a lot less on the y-axis, indicating the car is slowing down. So now, take the time on your own to answer these questions. What does a steeper slope mean about the motion of the object? For A. What would it mean about the motion of the object if the slope were 0, or that it was a flat line? And C, what would it mean if the slope were negative? Now, for your last challenge in this lesson, I want you to use a new color to combine position and time for your distracted driver. Plot the interceptions for each important time interval. You should have 4. This will be your distracted driver in a different color than your not distracted driver. Work with a partner. Draw the lines between the points. and add the obstacle somewhere in the same place on the y-axis, where do you think the obstacle should be in this graph? So let's discuss that before I get you into your challenge. What are your ideas? Where should the obstacle be on our y-axis? What position will it have? You might say the obstacle, since it did not hit the car for our not distracted driver, might appear somewhere up here, and that its position is constant as it does not change over time. And we might also say it appeared at T1 or just about the same time in both videos. How would you draw any of these lines differently to more accurately show the change? Was this a steady decrease in speed, or would you show this more like a curve or a positive curve? Or would you show this like that type of curve or this type of line? How might you make these lines more realistically show how the speed actually changed during this interval? Would you do something like this? Or would you do maybe something more like that? What do you think? Add those changes and the obstacle to your graph, and then add the obstacle also to your graph of the distracted driver. Now that your graphs are done, you've had a chance to think it through with your partner. What differences did you notice that could explain why being distracted increases the likelihood of a vehicle collision? Finally, I'd like you to add your own thoughts about this question. What else could increase a driver's reaction time other than whether the driver's distracted or not?